On December 30th, 1958, at 4:35 p.m., a chemical operator at Los Alamos Scientific Laboratory's plutonium recovery facility initiated a stirring sequence in a 225-gallon stainless steel solvent-treating tank. The operation was routine. Identical procedures had been performed without incident for 7.5 years across thousands of processing cycles. The facility processed dilute solutions containing less than 0.1 grams per liter of plutonium, well below any criticality concern. Equipment responded normally. Phases separated as expected. Instrumentation indicated standard operating conditions. Yet beneath the surface, an invisible accumulation had been building. Over 7.5 years of operation, the irrecoverable loss assumed to go down the drain had instead collected within the system. 3.27 kilograms of plutonium concentrated in an organic solvent layer floating above an aqueous phase. The geometry was barely subcritical, a 5-inch thick disk with an estimated critical thickness of 5.5 inches. The operator followed training precisely. The stirrer functioned as designed. The only variable was the hydrodynamics of phase mixing. When the stirrer blades forced aqueous solution upward along the tank walls, displacing the outer portion of the solvent layer and thickening the central portion by approximately 0.4 inches, the geometry crossed the critical threshold. The system reported normal conditions right until the moment 1.5x 1017 fissions occurred in less than 2 seconds. This was not operator error or equipment failure. This was the inevitable result of a mass balance assumption that remained unverified for years. The question that emerges from this sequence is fundamental to process safety. How does a system designed to prevent criticality through dilute concentrations and geometry control create the exact conditions that guarantee it? A plutonium processing facility conducted routine inventory operations that had been performed safely for 7.5 years. Standard procedures were followed. Equipment functioned as designed. Yet, an accumulation of 3.27 kilograms of plutonium in an organic solvent layer created a barely subcritical configuration that required only stirring, a normal process step, to achieve criticality. This analysis examines how operational assumptions, geometry constraints, and material accumulation combine to create conditions where following procedure guaranteed failure. The Los Alamos Plutonium Recovery Facility operated under a fundamental safety premise that had governed nuclear processing operations since the early 1950s. Dilute concentrations provide inherent protection against criticality regardless of system geometry or inventory accumulation. This principle, embedded in facility design, procedures, and operator training, assumed that maintaining plutonium concentrations below 0.1 grams per liter would prevent critical configurations under any conceivable processing scenario. The assumption appeared robust, supported by decades of successful operations across multiple facilities and validated by criticality safety calculations that showed enormous safety margins at such low concentrations. The facility's design reflected this philosophy through its process flowsheet and equipment selection. Large volume vessels, including the 225-gallon stainless steel solvent-treating tank that would later become the site of the December 30 incident, were permitted specifically because the dilute concentration principle eliminated geometry concerns. The tank's 38-inch diameter and substantial height created significant volume for processing operations while maintaining what appeared to be conservative safety margins. Design engineers calculated that even if plutonium somehow concentrated beyond expected levels, the large geometry would provide sufficient neutron leakage to maintain subcriticality. The plutonium recovery process itself relied on tributyl phosphate, TBP, solvent extraction to separate and concentrate plutonium from lean residues. Solutions entering the process typically contained less than 0.1 grams per liter of plutonium, along with traces of americium and various fission products from upstream recovery operations. The TBP carried in an organic solvent, selectively extracted plutonium through batch operations followed by back extraction into aqueous phases that were subsequently concentrated through evaporation. The resulting concentrated solutions, containing plutonium at a few grams per liter, were then fed back into earlier recovery stages for further processing. This process complexity introduced factors that the original safety philosophy had not fully anticipated. TBP undergoes hydrolysis under the combined effects of heat, nitric acid, and alpha particle radiation, producing mono and dibutyl phosphates that form tightly bound plutonium complexes. These hydrolysis products accumulated over time, requiring periodic precipitation from the TBP solvent mixture. The precipitated plutonium-rich solids were filtered and sent to other processing areas, but the efficiency of this removal process was never comprehensively verified through mass balance accounting. The safety case for large geometry vessels rested on several interconnected assumptions that appeared individually reasonable but created systematic vulnerabilities when considered collectively. First, the mass balance assumption held that plutonium losses were truly irrecoverable, that material not explicitly accounted for had permanently exited the system through drain lines, filtration losses, or other irreversible pathways. Second, the chemistry assumption maintained that the dilute aqueous processing environment would prevent significant plutonium concentration in any single location. Third, the operational assumption expected that standard procedures would maintain these conditions indefinitely, through routine inventory and cleaning cycles. Each assumption contained elements of truth that masked its limitations. Plutonium losses did occur through multiple pathways, and the majority of unaccounted material likely did exit the system permanently. The aqueous processing environment did maintain low concentrations in most system locations most of the time. Standard procedures did successfully prevent criticality for 7.5 years across thousands of processing cycles. However, the assumptions failed to account for the cumulative effect of small retentions across extended operating periods and the preferential accumulation mechanisms inherent in the solvent extraction process. The instrumentation and control philosophy reflected these underlying assumptions through measurement strategies that focused on process optimization rather than safety verification. Temperature, pressure, and flow measurements provided operators with the information needed to maintain efficient extraction and separation operations. Chemical analysis confirmed plutonium concentrations in product streams and verified that waste streams met disposal criteria. However, the control system included no continuous measurement of plutonium inventory within individual vessels, no geometric monitoring of phase interfaces, and no trending analysis of cumulative mass balance discrepancies. Training programs emphasize the hazards most familiar to operators from previous incidents and near misses. Handling concentrated plutonium solutions, preventing excessive accumulation in small geometry vessels, and maintaining proper chemical conditions for efficient extraction. The curriculum included extensive coverage of criticality safety principles, but the focus remained on scenarios involving deliberate concentration operations rather than inadvertent accumulation through normal processing. Operators learned to recognize and respond to concentration hazards while receiving less preparation for the subtle geometric and inventory hazards that could develop over extended periods. The regulatory framework governing the facility reinforced these assumptions through inspection criteria and safety reviews that emphasized procedural compliance and concentration control. Regulatory oversight focused on verifying that operators followed approved procedures, that chemical analyses confirmed expected concentration ranges, and that safety systems functioned as designed. The oversight process included periodic reviews of criticality safety analyses, but these reviews concentrated on verifying calculations rather than challenging underlying assumptions about process behavior over extended operating periods. The facility's operational history provided apparent validation for the design philosophy. Over 7.5 years of operation, the plutonium recovery process had successfully handled thousands of batches without experiencing criticality or approaching conditions that raised safety concerns. Mass balance reconciliation showed acceptable agreement between input materials and output products, with discrepancies attributed to measurement uncertainty and expected system losses. The consistent success of operations reinforced confidence in the underlying safety assumptions and discouraged detailed investigation of small anomalies that might have revealed accumulation trends. The December 30 incident occurred during a routine physical inventory that required interrupting normal process flows and evaluating residual materials in all vessels for plutonium content. This inventory process, conducted annually to satisfy regulatory requirements and internal accounting controls, involved systematic emptying and cleaning of all process equipment, followed by detailed analysis of removed materials. The procedure was well established and had been completed successfully in previous years without incident or unexpected findings. However, the inventory procedure contained a critical decision point that would prove decisive: whether to process materials from multiple vessels individually or to combine them for more efficient handling. The written procedure specified individual processing to maintain control over batch compositions and to ensure that any unusual conditions could be traced to specific sources. Individual processing also minimized the total inventory of plutonium in any single vessel at any given time, consistent with the Defense in-depth philosophy underlying facility safety analysis. The organic extraction process that concentrated plutonium into the solvent-treating tank represented the convergence of normal chemical operations with accumulated material that violated fundamental design assumptions. The acidification step, essential for breaking the caustic stabilized emulsion, created optimal conditions for plutonium extraction from the solid residues into the organic phase. The phase separation that followed, occurring naturally as designed, concentrated the extracted plutonium in the upper organic layer, while leaving the bulk aqueous phase with minimal plutonium content. The final configuration in the solvent-treating tank immediately before the incident represented a textbook illustration of how conservative design assumptions could be systematically violated through the cumulative effect of normal operations. The 42.2-gallon organic layer contained 3.27 kilograms of plutonium at a concentration of 20 grams per liter, far exceeding both the 0.1 gram per liter design basis and the concentration thresholds that would have triggered additional safety controls. The 5-inch thickness of this layer approached the calculated critical thickness of 5.5 inches for this plutonium concentration and geometry, creating a configuration that was barely subcritical and sensitive to small geometric perturbations. The mass balance discrepancy that enabled this accumulation had developed gradually over the facility's operating history, masked by measurement uncertainties and the complexity of tracking materials through multiple process stages. The 3.27 kilograms of plutonium represented approximately 0.04% of the total plutonium processed through the facility over 7.5 years, a discrepancy well within the expected range of measurement uncertainty and acceptable losses. However, this apparently insignificant discrepancy, concentrated in a single location through the normal operation of the extraction process, created exactly the conditions that the original safety philosophy was designed to prevent. The December 30, 1958 criticality incident emerged from a complex interaction between established procedures, operational practices, and human factors that had evolved over years of successful operations. While the fundamental design assumptions created the potential for plutonium accumulation, the specific sequence of events that led to criticality required a convergence of latent conditions that transformed routine inventory operations into a critical configuration. These conditions, individually reasonable and consistent with established practice, combined to eliminate the safety barriers that had protected the facility for 7.5 years. The physical inventory procedure that initiated the incident sequence was well established and had been performed successfully in previous years. The standard protocol required that each vessel containing fissile material be emptied and cleaned individually, with thorough analysis of removed solutions and solids to establish plutonium content for accounting purposes. This individual processing approach maintained control over batch compositions, ensured traceability of materials to specific sources, and minimized the total plutonium inventory in any single vessel during the inventory process. However, the procedure contained sufficient flexibility to accommodate operational judgments about efficiency and logistics. The written instructions specified the general approach and safety requirements, but left implementation details to the supervisor and operators conducting the inventory. This flexibility, designed to accommodate varying plant conditions and material distributions, created decision points where operational considerations could modify the intended safety approach Without explicit recognition that safety margins were being reduced, the critical decision to combine materials from multiple vessels for processing efficiency represented a departure from the standard individual batch approach that had characterized previous inventories. According to the investigation findings, plutonium-rich solids that normally would have been handled separately were washed from 2 vessels into a large vessel containing dilute, aqueous, and organic solutions. This consolidation, motivated by the practical advantages of processing related materials together and reducing the total time required for inventory completion, eliminated the batch separation that served as a key safety barrier. The operator implementing this modified approach possessed extensive experience with the plutonium recovery process and had demonstrated consistent adherence to safety procedures throughout his tenure at the facility. His reputation for reliability and technical competence had earned the trust of supervisors and colleagues, contributing to an environment where his procedural modifications were accepted without detailed review. The investigation noted that this operator knew the processes he was carrying out and the reasons for them, and had always followed directions in previous operations. The specific modifications introduced during the December 30 inventory reflected a pattern of operational optimization that had developed gradually over the facility's operating history. Small procedural adjustments, implemented to improve efficiency or address specific material handling challenges, had become accepted practice when they proved successful and created no apparent safety concerns. These modifications represented the natural evolution of operating procedures in response to practical experience, but they occurred without formal review of their cumulative impact on safety margins. The training and qualification program for plutonium recovery operations emphasized hazard recognition and procedural compliance, but provided limited guidance for evaluating the safety implications of procedural modifications. Operators learned to recognize and respond to established hazard scenarios. Concentrated solutions, improper batch sizes, equipment malfunctions, but received less preparation for assessing the safety significance of operational changes that fell within general procedural guidelines. The training focused on preventing known hazards, rather than developing the analytical tools needed to identify new or evolving risks. The supervision and oversight structure that governed inventory operations reflected the confidence built through years of successful performance and the complexity of simultaneously managing multiple process areas during facility shutdown periods. Supervisors necessarily relied on experienced operators to execute detailed procedures while maintaining awareness of overall progress and any significant deviations from standard practice. This distributed decision-making approach worked effectively under normal conditions, but created potential gaps when operator modifications interacted with conditions that fell outside previous experience. The material handling sequence that concentrated plutonium in the solvent-treating tank began with the transfer of approximately 40 gallons of solution from a large vessel that had been used to collect washings from other process equipment. This material contained both aqueous and organic phases with suspended plutonium, bearing solids that had accumulated during previous processing cycles. The transfer operation, performed using standard procedures and equipment, moved this material into the solvent-treating tank that already contained about 80 gallons of caustic-stabilized aqueous organic emulsion from TBP hydrolysis product precipitation operations. The addition of 13 gallons of concentrated nitric acid to wash remaining solids from the source vessel into the solvent-treating tank represented standard practice for ensuring complete material recovery during inventory operations. The acid wash, essential for dissolving and mobilizing plutonium-bearing residues, created the chemical conditions necessary for effective extraction into the organic phase. The procedure specified that transfers into the tank be followed by air sparging to ensure thorough mixing, a step designed to promote complete chemical reactions and uniform material distribution. The air sparging operation that followed the material transfers functioned exactly as designed, breaking the caustic-stabilized emulsion through acidification and promoting extraction of plutonium from the solid residues into the organic solvent phase. The chemical reactions proceeded efficiently, with phase separation occurring within the expected time frame of approximately 2.5 minutes. The process chemistry worked precisely as intended, concentrating plutonium in the organic phase while leaving the bulk aqueous solution with minimal plutonium content. The resulting phase distribution created conditions that fundamentally violated the facility's safety basis without generating any indication that unusual conditions had developed. The 87.4 gallons of aqueous solution contained only 40 grams of plutonium at a concentration of 0.46 grams per liter, slightly above the nominal 0.1 gram per liter design basis, but well within the range considered safe for large geometry vessels. However, the 42.2 gallons of organic solution contained 3.27 kilograms of plutonium at a concentration of 20 grams per liter, creating a 5-inch thick layer that approached the critical thickness for this geometry. The absence of any instrumentation capable of detecting this configuration created a fundamental blind spot in the facility's safety systems. Standard process monitoring focused on temperatures, pressures, and bulk chemical compositions rather than detailed geometric analysis of phase interfaces or plutonium distribution within individual vessels. The control room indicators showed normal operating conditions throughout the material transfer and phase separation sequence, providing no warning that a potentially critical configuration had developed. The decision to activate the stirring system represented the final step in a logical operational sequence that followed established procedures for material processing. Stirring was routinely used to ensure complete mixing during chemical operations, to promote phase contact for extraction efficiency, and to maintain uniform conditions within process vessels. The operator's decision to start the stirrer reflected standard practice for this type of operation and was consistent with the procedural guidance for material processing during inventory operations. The equipment design and operating instructions provided no indication that stirring could create hazardous conditions under any conceivable process scenario. The stirrer motor and blade assembly were sized for the tank geometry and typical fluid properties encountered during normal operations. The control system included standard safety interlocks to prevent equipment damage but no provision for criticality, safety monitoring, or prevention during stirring operations. The design assumed that dilute concentrations would prevent criticality regardless of mixing patterns or geometric perturbations. The organizational context surrounding the December 30 inventory reflected broader patterns in the nuclear industry's approach to operational safety during the 1950s. Safety management focused primarily on compliance with established procedures and maintenance of known safe conditions, rather than continuous evaluation of changing risk profiles or systematic analysis of procedural modifications. The success-based confidence that characterized facility operations was typical of the industry's approach to managing low-probability, high-consequence risks through demonstrated performance, rather than analytical assessment. The human factors environment that enabled the incident sequence included several elements that were individually reasonable but collectively reduced the effectiveness of safety barriers. The experienced operator's modification of standard procedures reflected confidence built through years of successful performance and a practical understanding of process requirements. The supervisory acceptance of these modifications demonstrated trust in operator competence and recognition of the practical benefits of operational flexibility. The absence of specific guidance for evaluating procedural changes reflected the general industry assumption that experienced personnel could safely adapt procedures within established boundaries. The investigation findings identified specific organizational and procedural factors that contributed to the incident, but avoided the hindsight bias that might characterize these factors as obviously deficient. The special committee appointed by the Atomic Energy Commission concluded that the accident was directly attributable to errors on the part of the operator, who was killed, but acknowledged the complexity of the factors that led to these errors. The committee recognized that closer supervision might have prevented the accident while noting that the operator was experienced, reliable, and following what he understood to be appropriate procedures. The systemic implications of the incident extended beyond the specific procedural and human factors issues to encompass broader questions about the adequacy of safety philosophies based on historical performance rather than comprehensive hazard analysis. The successful completion of inventory operations in previous years had reinforced confidence in existing procedures while masking the gradual accumulation of conditions that made criticality possible. The incident demonstrated that complex systems can accumulate latent hazards through normal operations that fall within established safety boundaries, but combine in unexpected ways to create new risk profiles. The December 30, 1958 criticality incident began with a routine operation that had been performed successfully thousands of times throughout the facility's operating history. At approximately 4:35 p.m., chemical operator K initiated the stirring mechanism in the solvent treating tank to ensure uniform mixing of the materials that had been transferred during the inventory process. The stirrer motor responded normally, the blade assembly engaged properly, and the initial fluid motion proceeded exactly as designed. Nothing in the operator's training, experience, or the available instrumentation suggested that this standard operation would produce anything other than the expected mixing and homogenization of tank contents. The physical configuration of materials in the 225-gallon 38-inch diameter stainless steel tank at the moment of stirrer activation represented the culmination of the accumulation and concentration processes that had developed over 7.5 years of facility operations. The tank contained two distinct phases: 87.4 gallons of aqueous solution in the lower portion with 40 grams of plutonium at a concentration of 0.46 grams per liter, and 42.2 gallons of organic solution in the upper portion containing 3.27 kilograms of plutonium at a concentration of 20 grams per liter. Additional plutonium-bearing solids, totaling approximately 60 grams, were suspended in both phases and at the interface between them. The organic layer configuration created conditions that were barely subcritical according to later criticality calculations. The 5-inch thickness of the organic phase approached the estimated critical thickness of 5.5 inches for this plutonium concentration and geometry, accounting for the effects of neutron poisons and the tank diameter. The investigators estimated that this configuration was roughly $5 subcritical, a margin that appeared substantial in absolute terms, but represented a narrow safety buffer given the uncertainties in plutonium distribution and the potential for geometric perturbations during mixing operations. The hydrodynamic effects of stirrer activation created precisely the geometric changes necessary to transform the barely subcritical configuration into a critical assembly. The stirrer blades, rotating in the lower aqueous phase, forced fluid upward along the tank walls in a pattern consistent with standard mixing correlations for this equipment design. This upward flow of aqueous solution displaced the outer portions of the organic layer, causing the plutonium-rich organic phase to flow inward and thicken in the central region directly above the stirrer assembly. The criticality calculations performed after the incident indicated that an average increase in organic layer thickness of approximately 0.4 inches, corresponding to an average radius decrease of about 0.6 inches, would be sufficient to achieve a critical configuration. This geometric change fell well within the range of fluid perturbations expected during normal stirring operations and represented a modification that would occur routinely whenever the stirrer was activated under similar conditions. The transition from subcritical to critical geometry occurred through normal fluid mechanics with no unusual equipment behavior or abnormal process conditions. The nuclear excursion that followed stirrer activation proceeded as a single sharp burst without the oscillatory behavior that characterized some other criticality incidents. The rapid achievement of criticality was followed almost immediately by self-termination as the violent fluid motion generated by the nuclear energy release disrupted the critical geometry and distributed the plutonium-rich material throughout the tank volume. The investigators estimated that the total number of fissions in the burst was approximately 1.5 x 10 to the power of 17, based on radiochemical analysis of molybdenum-98 concentrated in the aqueous phase. The operator's immediate experience of the criticality provided clear evidence of the violent nature of the nuclear excursion. Accounts of the incident describe a blue flash and a muffled report that occurred within seconds of stirrer activation. The operator, who was looking into a sight glass at the top of the tank from a position on a two-step ladder, was knocked backward by the shock wave and fell to the floor. The physical displacement of the tank, approximately 0.75 inches at its supports, demonstrated the significant mechanical forces generated by the rapid energy release in a confined volume. The operator's actions immediately following the excursion reflected both the disorienting effects of radiation exposure and his training for responding to abnormal conditions. After regaining his footing, he apparently turned the stirrer motor off and then on again, possibly to verify equipment status or in confusion about the cause of the disturbance. This second activation produced what the operator described as a rumbling sound that was likely the normal stirrer operation under the altered fluid conditions created by the initial excursion. No evidence suggested a second nuclear burst, and radiation detector traces were consistent with a single excursion hypothesis. The immediate physical effects on the operator provided dramatic evidence of the radiation dose received during the brief exposure period. Within minutes of the incident, Operator K displayed symptoms of acute radiation syndrome including ataxia, disorientation, and an inability to stand without support. His repeated statement that he was burning up reflected both the physiological effects of massive radiation exposure and his intuitive recognition that something extraordinary had occurred. The rapid onset of these symptoms indicated a radiation dose far exceeding any previous occupational exposure recorded at the facility. The facility's radiation detection systems responded to the nuclear excursion exactly as designed, providing confirmation of the abnormal radiological conditions and initiating emergency response procedures. A radiation alarm located 17.5 feet from the incident tank activated immediately, having been set to trigger at 10 milliroentgens per hour. This alarm was connected to indicating instruments and provided both local and remote notification of the elevated radiation levels. The activation of this system at 4:35 p.m. provided precise timing for the incident and confirmed that significant quantities of radiation had been released. The two additional operators working in adjacent areas experienced the incident as an unexpected but clearly abnormal event that required immediate investigation and response. Operator D, located approximately 40 feet away in an adjoining room, saw the reflection of the blue flash on the walls and heard the report of the nuclear excursion. His immediate response, leaving his workstation to investigate the disturbance, reflected both his recognition that something unusual had occurred and his training to provide assistance when abnormal conditions developed. The discovery of Operator K in a disoriented state outside the building triggered the emergency response procedures that had been developed for radiation incidents. The immediate assumption that he had suffered chemical contamination rather than radiation exposure reflected the expectation that criticality was impossible under the facility's operating conditions. This initial misdiagnosis led to appropriate first aid measures, emergency shower and clothing removal, that were beneficial regardless of the actual exposure mechanism, but did not address the specific medical requirements for acute radiation syndrome. The physical examination of the accident tank and surrounding area revealed additional evidence of the nuclear excursion's violence, while confirming that the containment boundary had remained intact. The tank was not bolted to the floor, and the tangential shift of one supporting leg was clearly visible because the initial position was outlined by the latest coat of floor paint. The tank appeared to have pivoted about the opposite support, demonstrating the asymmetric forces generated by the rapid energy release. Despite this mechanical displacement, the tank structure remained intact with no rupture or release of plutonium to the environment. The immediate radiological assessment of the area surrounding the accident tank confirmed the magnitude of the nuclear excursion while demonstrating the effectiveness of the containment design. Initial radiation readings taken within hours of the incident showed contact dose rates at the tank of approximately 20 roentgens per hour, with readings at 25 feet decreasing to manageable levels for emergency response activities. The spatial distribution of radiation levels was consistent with the hypothesis of a single intense burst, followed by mixing that distributed the activated materials throughout the tank volume. The plant evacuation that followed the incident reflected both the magnitude of the radiation release and the uncertainty about potential follow-on effects. The entire facility was evacuated by 4:35 p.m., with personnel accounting and radiological surveys conducted to ensure that no additional exposures had occurred. This conservative response demonstrated the effectiveness of emergency procedures while providing the controlled conditions necessary for detailed assessment of the incident's scope and implications. The material balance information available immediately after the incident provided the first quantitative evidence of the plutonium inventory that had accumulated in the solvent-treating tank. While detailed analysis would require days of careful measurement and sampling, initial estimates based on transfer records and previous inventory data suggested that significantly more plutonium was present than would be expected from the routine processing operations. This preliminary assessment began the process of reconstructing the material flow sequence that had created the critical configuration. The immediate technical assessment of the incident focused on understanding the mechanism that had enabled criticality while ensuring that similar conditions could not develop in other facility locations. The investigation team, assembled within hours of the incident, included criticality safety experts, process engineers, and health physics personnel, with the expertise needed to evaluate both the immediate hazards and the systemic implications of the event. Their initial focus on material accountability and geometric analysis established the framework for the comprehensive investigation that would follow. The divergence between the operator's reasonable expectations and the actual system state represented the fundamental mechanism that enabled the December 30 incident. Every aspect of the operation, material transfers, chemical processing, phase separation, and stirring, proceeded according to established procedures and produced the expected immediate results. The instruments showed normal conditions, the equipment functioned properly, and the process chemistry worked as designed. Yet these normal operations had created exactly the conditions that the facility's safety philosophy was designed to prevent, demonstrating how conservative assumptions could be systematically violated through the cumulative effect of routine activities. The nuclear criticality that occurred at 4:35 p.m. on December 30, 1958, represented the inevitable physical consequence of a precisely defined set of geometric and material conditions that had developed through normal operational processes. The failure chain that culminated in the excursion followed predictable nuclear physics principles, with each step proceeding according to well-established theoretical relationships between plutonium mass, geometry, concentration, and neutron multiplication. Understanding this chain requires detailed examination of the nuclear physics mechanisms that transformed a barely subcritical configuration into a prompt critical assembly within seconds of stirrer activation. The initial neutron multiplication state in the solvent-treating tank immediately before stirrer activation can be reconstructed through criticality calculations using the known material distribution and geometric configuration. The 42.2 gallons of organic solution containing 3.27 kilograms of plutonium at 20 grams per liter formed a cylindrical layer approximately 5 inches thick in the 38-inch diameter tank. This geometry, with plutonium-239 as the primary fissile isotope and the organic solvent providing moderation, created a neutron multiplication factor, K effective, that approached but did not exceed unity. The criticality calculations performed after the incident utilized established nuclear data and computational methods to determine the critical dimensions for this specific material composition and geometry. For an infinite cylinder of this plutonium concentration and organic solvent, the critical thickness would be approximately 5.5 inches, accounting for neutron absorption by impurities and the moderating effect of the organic medium. The finite geometry of the tank, with its 38-inch diameter and the presence of aqueous solution above and below the organic layer, modified this critical dimension through neutron leakage effects and geometric coupling between regions. The investigators estimate that the configuration was roughly $5 subcritical, reflected the narrow margin between the actual 5-inch thickness and the critical thickness of approximately 5.5 inches. In reactor physics terminology, $1 of reactivity represents the delayed neutron fraction, approximately 0.0065 for plutonium-239 systems, which defines the boundary between delayed critical and prompt critical conditions. A system that is $5 subcritical has a neutron multiplication factor of approximately 0.97, indicating that each neutron generation produces 97% as many neutrons as the previous generation, leading to an exponentially decreasing neutron population over time. The hydrodynamic analysis of stirrer operation provided the crucial link between normal equipment function and the geometric perturbation necessary to achieve criticality. The stirrer assembly, consisting of a motor-driven shaft with blade attachments designed for the tank geometry and typical fluid properties, created a specific flow pattern when activated in the two-phase system present on December 30th. The rotating blades, positioned in the lower aqueous phase, imparted angular momentum to the fluid while generating radial and axial flow components through centrifugal and pumping actions. The upward flow of aqueous solution along the tank walls, driven by the pumping action of the stirrer blades, displaced the organic layer inward through simple fluid displacement mechanisms. As the aqueous phase moved upward around the tank periphery, the organic phase was forced to flow radially inward to maintain volume balance within the confined geometry of the tank. This radial compression increased the thickness of the organic layer in the central region, while reducing its thickness near the tank walls, creating a non-uniform distribution that maximized the neutron multiplication in the region of greatest thickness. The geometric changes necessary to achieve criticality occurred within the normal operating envelope of the stirring equipment. Computational fluid dynamics analysis of similar systems indicates that radial compression of 0.5 to 1 inches would be typical for the stirrer design and operating speed when mixing phases with different densities. The investigators calculated that an average increase in organic layer thickness of approximately 0.4 inches, corresponding to an average radius decrease of 0.6 inches, would be sufficient to achieve a critical configuration under the existing material conditions. The transition from delayed critical to prompt critical occurred rapidly as the geometric compression continued during the initial seconds of stirrer operation. When the neutron multiplication factor reached unity, K effective equal to 1, the system achieved a self-sustaining chain reaction with the neutron population maintained by delayed neutrons from previous fission events. As geometric compression continued beyond this point, the multiplication factor exceeded unity by more than the delayed neutron fraction, creating a prompt critical condition where the neutron population could increase exponentially on the prompt neutron generation time of approximately 10⁻⁵ seconds. The prompt critical excursion proceeded according to the well-established physics of nuclear kinetics in liquid systems. The rapid increase in neutron population led to an exponential rise in fission rate and energy release, with the power level increasing by orders of magnitude within milliseconds. The energy deposition in the organic solution created rapid heating and vapor formation, generating internal pressure that violently disrupted the fluid configuration and terminated the nuclear reaction through geometric changes that reduced the neutron multiplication below unity. The self-limiting nature of the excursion reflected the inherent shutdown mechanisms present in liquid fissile systems. Unlike solid reactor cores where geometric changes require mechanical forces or thermal expansion, liquid systems can undergo rapid geometric reconfiguration through hydrodynamic effects driven by the energy release itself. The violent mixing that terminated the December 30 excursion distributed the concentrated plutonium throughout the tank volume, reducing local concentrations and eliminating the geometric conditions necessary for sustained criticality. The total energy release during the excursion can be estimated from the measured fission product inventory and the known energy per fission for plutonium-239. The radiochemical analysis of molybdenum-98, concentrated primarily in the aqueous phase after the incident, indicated approximately 1.5 x 10 to the power of 17 total fissions during the burst. With an energy release of approximately 200 million electron volts per fission, the total energy deposited in the system was approximately 4.8 x 10 to the power of 9 joules, equivalent to roughly 1.1 kilograms of TNT explosive energy. The mechanical effects observed after the incident, including the displacement of the 225-gallon tank by approximately 0.75 inches and the operator being knocked from his ladder, were consistent with this energy release occurring in a confined liquid system. The rapid conversion of nuclear energy to thermal energy and then to mechanical work through vapor formation and pressure generation, created impulse forces sufficient to move the massive tank and generate the shockwave that affected personnel in the immediate area. The investigators noted that despite these violent mechanical effects, the tank structure remained intact with no rupture or breach of containment. The radiation field generated by the nuclear excursion reflected both the immediate effects of the fission process and the longer-term consequences of fission product formation and activation of structural materials. The prompt radiation consisted primarily of gamma rays and neutrons released directly during the fission process, creating the intense but brief exposure that affected the operator looking into the tank. The delayed radiation from fission product decay and activated materials in and around the tank created the persistent radiation field that required evacuation of the facility and careful planning for subsequent response activities. The spatial distribution of radiation exposure provided additional evidence for the location and nature of the nuclear excursion. The operator positioned directly above the tank received an estimated dose of 12,000 roentgens, while the two operators in adjacent areas received significantly lower doses of 134 and 53 roentgens respectively. This exposure pattern was consistent with a localized source in the upper portion of the tank, where the organic layer containing the concentrated plutonium was located, and demonstrated the strong geometric dependence of radiation exposure from point sources. The neutron dose component of the total exposure was determined through measurement of induced radioactivity in the operator's body and clothing, as well as in nearby materials such as brass buttons and chemical reagents. Neutron activation of sodium-23 to form sodium-24 in blood and body tissues provided a direct measurement of neutron flux, while activation of other materials confirmed the magnitude and spatial distribution of the neutron field. These measurements indicated that both neutrons and gamma rays contributed significantly to the total dose, with the neutron component providing unique information about the nuclear nature of the event. The absence of significant plutonium contamination outside the tank demonstrated the effectiveness of the containment design while confirming that the primary hazard was radiation exposure rather than internal contamination. Air sampling and surface contamination surveys conducted immediately after the incident showed no detectable plutonium release to the work area, indicating that the tank had successfully contained the liquid contents despite the violent mechanical disruption. This containment performance was crucial for limiting the scope of contamination and enabling subsequent recovery operations. The material redistribution within the tank following the excursion could be inferred from subsequent radiation surveys and sampling operations. Gamma radiation measurements around the tank exterior showed a relatively uniform distribution compared to the highly localized pattern that would be expected from the original organic layer configuration. This redistribution was consistent with violent mixing that had dispersed the plutonium throughout the tank volume, eliminating the geometric concentration that had enabled the initial criticality. The chemical analysis of materials recovered from the tank during subsequent cleanup operations confirmed the physical mixing that had occurred during the excursion. While detailed sampling would require careful planning to minimize exposure and ensure representative measurements, initial results showed plutonium distributed between both aqueous and organic phases in proportions that differed significantly from the pre-incident configuration. This redistribution provided additional evidence for the violent fluid motion that had terminated the nuclear reaction. The unique characteristics of the December 30 incident, compared to other criticality accidents in the nuclear industry, reflected the specific combination of material, geometry, and disturbance mechanism present in the solvent-treating tank. Unlike criticality incidents involving solid materials or simple aqueous solutions, this event occurred in a complex two-phase system where normal processing operations created the geometric changes necessary to achieve critical configurations. The incident demonstrated that liquid systems could undergo rapid transitions from safe to critical conditions through routine operational activities. The implications of the failure chain for nuclear criticality safety extended beyond the specific circumstances of the plutonium recovery facility to encompass broader questions about the adequacy of safety analyses based on static geometric calculations. The incident showed that dynamic processes, fluid mixing, phase redistribution, and geometric perturbation could systematically defeat safety measures designed for static configurations. This recognition would influence subsequent approaches to criticality safety analysis, with greater emphasis on potential geometric changes during normal and abnormal operations. The immediate aftermath of the December 30 criticality incident presented facility management and emergency response personnel with an unprecedented challenge: safely managing a plutonium processing system in an unknown and potentially unstable configuration while protecting personnel from significant radiation hazards. The nuclear excursion had terminated through self-limiting mechanisms, but the distribution of plutonium within the solvent-treating tank remained uncertain, creating the possibility of additional criticality events if materials were disturbed inappropriately. The development of stabilization procedures required conservative engineering approaches that assumed worst-case conditions while enabling the systematic recovery of materials and restoration of safe configurations. The decision to fabricate a dedicated withdrawal system for removing solutions from the accident tank reflected both the magnitude of the radiation hazards and the uncertainty about plutonium distribution within the vessel. Within hours of the incident, facility engineers designed and constructed a bank of 10 withdrawal cylinders with diameters of 6 and 5 inches, specifically sized to maintain favorable geometry for criticality safety, regardless of the plutonium concentration that might be encountered during material removal. These cylinders were positioned approximately 100 feet from the accident site, providing both radiation shielding through distance and geometric separation to prevent neutron coupling between the accident tank and the storage array. The engineering analysis supporting the withdrawal system design incorporated lessons learned from the incident itself while maintaining conservative assumptions about unknown conditions within the tank. The criticality safety evaluation assumed that plutonium concentrations could approach the maximum values observed before the incident, requiring geometry control as the primary safety mechanism for material handling operations. The individual cylinder design ensured that even complete filling with concentrated plutonium solution would remain subcritical through favorable geometry, eliminating dependence on concentration measurements or administrative controls during the emergency response phase. The mechanical systems required for material transfer presented additional challenges due to the need for remote operation and the potential for equipment contamination during withdrawal operations. The transfer line connecting the storage cylinders to the bottom outlet valve of the solvent-treating tank was designed as a disposable system that could be abandoned if contamination levels made recovery impractical. The vacuum transfer method, selected to minimize the potential for creating pressure differentials that could disturb remaining materials in the tank, required careful coordination between the withdrawal rate and the monitoring of tank conditions. The decision to operate the tank outlet valve remotely using a 10-foot extension handle from behind temporary shielding demonstrated the conservative approach adopted for all operations involving direct interaction with the accident tank. This remote operation capability reflected both the significant radiation fields present at the tank location and the uncertainty about potential system responses to valve actuation. The temporary shielding, constructed from available materials and positioned to protect essential personnel during valve operations, provided additional confidence that emergency operations could be completed even if radiation conditions were worse than initially estimated. The radiation monitoring strategy developed for the withdrawal operations incorporated both area monitoring and material-specific measurements to track the progress of stabilization activities while ensuring personnel safety. Gamma-sensing instruments with remote readout capability were positioned to monitor solution levels within the withdrawal cylinders, providing continuous indication of transfer progress without requiring personnel access to high radiation areas. The maximum contact reading of approximately 1 Roentgen per hour at the cylinder locations confirmed that the withdrawal system design had successfully achieved the goal of distance-based radiation protection. The systematic approach to material withdrawal reflected careful planning to minimize the potential for creating new hazards while gathering information about the actual conditions within the tank. The vacuum transfer system allowed for controlled removal rates that could be adjusted based on radiation measurements and tank response, avoiding rapid changes that might destabilize remaining materials or create unexpected geometric configurations. Each 5-liter batch removed from the storage cylinders was sampled and analyzed to track changes in plutonium concentration and distribution, providing progressive insight into the effectiveness of the mixing that had occurred during the nuclear excursion. The chemical analysis results from successive withdrawal batches provided the first quantitative confirmation of the violent mixing that had terminated the nuclear excursion. Unlike the sharply stratified configuration present before the incident, with concentrated plutonium in the organic phase and minimal plutonium in the aqueous solution, the post-incident samples showed plutonium distributed throughout both phases in proportions that varied significantly from the original distribution. Table 1 in the investigation report documented plutonium concentrations ranging from 0.112 grams per liter in aqueous phases to 20.4 grams per liter in organic phases, with the bulk of the material showing concentrations well below the critical ranges that had existed immediately before the incident. The material balance verification conducted during the withdrawal process confirmed both the total plutonium inventory that had accumulated in the tank and the effectiveness of the containment systems in preventing release during the incident. The total plutonium recovered from the tank, 3.27 kilograms in organic phases, 40 grams in aqueous phases, and approximately 60 grams in suspended solids, matched the estimates developed from reconstruction of transfer operations and provided quantitative confirmation of the mass accumulation that had enabled the criticality. The fact that this total could be accounted for within measurement uncertainty demonstrated that no significant plutonium release had occurred despite the violent nature of the nuclear excursion. The detection of gamma activity in structural materials surrounding the tank provided additional evidence of the neutron flux magnitude during the incident while confirming the localized nature of the excursion. Scanning of the Type 347 stainless steel baffle located approximately 6 inches within the tank wall showed peak activity about 1 inch below the mid-plane of the original organic layer, consistent with neutron activation during the brief period when critical conditions existed. This activation pattern provided independent confirmation of both the location of the nuclear reaction and the rapid termination that had prevented sustained criticality. The absence of detectable plutonium contamination in areas surrounding the accident tank confirmed the effectiveness of the containment design while simplifying the scope of recovery operations. Air sampling conducted immediately after the incident and during subsequent operations showed no airborne plutonium above natural background levels, indicating that the tank had successfully contained all liquid contents despite the mechanical shock from the pressure pulse. Surface contamination surveys of floors, walls, and equipment in the work area similarly showed no detectable plutonium, confirming that the primary hazard was external radiation rather than contamination control. The progressive reduction in radiation levels around the tank during the withdrawal operations provided real-time confirmation that the stabilization approach was successfully eliminating the source terms responsible for area radiation fields. Initial contact readings at the tank of approximately 20 Röntgens per hour decreased systematically as materials were removed, reaching levels below 50 milliröntgens per hour at tank wall locations after completion of the withdrawal process. This reduction demonstrated both the effectiveness of the material removal operations and the absence of significant activation or contamination sources that would persist after plutonium removal. The engineering challenges associated with maintaining criticality safety during withdrawal operations required continuous evaluation of changing conditions as materials were removed and tank geometry evolved. The initial conservative assumptions about plutonium distribution had to be balanced against the practical requirements for completing withdrawal operations within reasonable timeframes while minimizing personnel exposure. The systematic sampling and analysis program provided the information needed to verify that actual conditions remained within the safety envelope established for the withdrawal system design. The coordination of withdrawal operations with ongoing facility activities presented additional management challenges due to the continued presence of plutonium processing operations in other areas of the complex. The emergency response had required evacuation of the immediate work area but not the entire facility, creating the need for careful interface management to prevent cross-contamination or interference between normal operations and emergency response activities, The establishment of controlled access zones and dedicated personnel assignments ensured that both emergency response and routine operations could continue without compromising safety or efficiency. The development of contingency procedures for potential complications during withdrawal operations reflected the recognition that unknown conditions within the tank could create unexpected challenges for material removal systems. Alternative approaches for handling high radiation materials, procedures for responding to equipment failures during remote operations, and protocols for managing unexpected changes in material behavior were developed and maintained in readiness throughout the withdrawal process. These contingency measures provided additional confidence that operations could be completed successfully, even if initial assumptions proved incorrect. The documentation and tracking systems established for withdrawal operations served both immediate operational needs and longer-term investigation requirements by providing detailed records of material compositions, radiation measurements, and operational parameters throughout the recovery process. Each batch withdrawal was documented with precise measurements of volume, plutonium content, radiation levels, and chemical composition, creating a comprehensive database for subsequent analysis of the incident mechanism and verification of theoretical calculations. This systematic approach to data collection ensured that maximum information value could be extracted from the emergency response activities. The successful completion of material withdrawal operations within 24 hours of the incident demonstrated both the effectiveness of conservative engineering approaches and the value of systematic emergency planning for low-probability, high-consequence events. The withdrawal of approximately 130 gallons of solution containing over 3 kilograms of plutonium was accomplished without additional personnel exposure or safety incidents, confirming that appropriate emergency response capabilities could be rapidly implemented even for unprecedented accident scenarios. The transition from emergency response to systematic investigation began immediately upon completion of material withdrawal operations, as the elimination of immediate hazards enabled detailed technical analysis of the incident mechanism and contributing factors. The material samples collected during withdrawal operations provided the foundation for chemical and radiological analyses that would reconstruct the precise conditions present before, during, and after the nuclear excursion. The radiation surveys conducted throughout the response period established baseline conditions for subsequent facility operations and confirmed the effectiveness of decontamination measures. The comprehensive forensic investigation that followed the December 30 criticality incident established a new standard for post-accident technical analysis in the nuclear industry, combining detailed material characterization, radiation measurements, and theoretical calculations to reconstruct the precise sequence of events that had enabled criticality in a system designed to prevent such occurrences. The investigation's findings provided not only a complete understanding of this specific incident, but also fundamental insights into the broader challenges of maintaining criticality, safety in complex processing systems where normal operations could systematically defeat conservative design assumptions. The radiochemical analysis of materials recovered from the solvent treating tank provided definitive confirmation of both the nuclear excursion's magnitude and the violent mixing that had terminated the critical reaction. The measurement of molybdenum-98 fission products, concentrated primarily in the aqueous phase following the incident, yielded a total fission count of approximately 1.5 times 10 to the power of 17. This value, derived from gamma spectroscopy analysis of samples collected during the withdrawal operations, represented direct physical evidence of the energy release during the brief critical period and validated theoretical calculations of the excursion's intensity. The spatial distribution of fission products within the tank provided additional forensic evidence for the mechanism of criticality termination through hydrodynamic mixing. Unlike the highly stratified plutonium distribution that had existed immediately before the incident, with concentrated material confined to the upper organic layer, the fission products were found distributed throughout both aqueous and organic phases in proportions that reflected the violent, fluid motion generated by the rapid energy release. This redistribution pattern confirmed that the nuclear excursion had created sufficient mechanical forces to disrupt the geometric configuration that had enabled criticality. The neutron activation analysis of structural materials surrounding the accident tank established an independent method for confirming both the location and intensity of the nuclear reaction. The Type 347 stainless steel baffle positioned approximately 6 inches within the tank wall showed measurable activation products consistent with neutron irradiation during the brief critical period. Detailed gamma scanning of this baffle revealed peak activity approximately 1 inch below the midplane of the original organic layer, providing precise spatial confirmation of where the critical reaction had occurred within the tank geometry. The activation measurements in the stainless steel structure also enabled quantitative assessment of the neutron flux magnitude during the excursion, supporting dose reconstruction efforts for the affected personnel and validating theoretical calculations of neutron production rates during prompt critical conditions. The measured activation levels were consistent with neutron fluxes of approximately 10 to the power of 14 neutrons per square centimeter, integrated over the brief duration of the critical excursion. These measurements provided crucial data for understanding the radiation environment that had existed during the incident and for developing improved shielding requirements for similar facilities. The detailed chemical analysis of plutonium distribution in recovered materials confirmed the effectiveness of the extraction chemistry that had concentrated plutonium in the organic phase, while revealing the complexity of the material balance discrepancies that had enabled accumulation over multiple years. Table 1 in the investigation report documented plutonium concentrations ranging from less than 0.1 grams per liter in some aqueous fractions to more than 20 grams per liter in organic phases, with the total plutonium inventory of 3.27 kilograms representing material that had been categorized as irrecoverable loss over 7.5 years of facility operations. The chemical form analysis provided crucial insights into the mechanisms that had enabled plutonium retention within the processing system despite procedures designed to ensure complete material recovery during routine operations. The plutonium found in the organic phase existed primarily as complexes with tributyl phosphate hydrolysis products. Mono and dibutyl phosphates formed through the combined effects of heat, nitric acid, and alpha radiation during normal processing operations. These tightly bound complexes were more difficult to remove through standard washing and extraction procedures, leading to gradual accumulation in locations where they could be concentrated through subsequent processing steps. The reconstruction of facility mass balance records over the 7.5-year operating period revealed systematic patterns in plutonium accountability that, while within acceptable limits for individual accounting periods, showed cumulative discrepancies that should have indicated material retention within the system. The investigation found that plutonium throughput totaling approximately 8,000 kilograms over the facility's operating history had resulted in cumulative losses of approximately 3.5 kilograms, a discrepancy of roughly 0.04% that fell well within the expected range of measurement uncertainty and acceptable process losses. However, this apparently insignificant discrepancy represented a systematic bias toward plutonium retention rather than the random measurement errors that had been assumed in mass balance evaluations. The concentration of this retained material in a single location through normal chemical processing operations had created exactly the conditions that the facility's safety analysis had assumed could not occur under any credible operational scenario. The investigation concluded that mass balance accounting systems based on statistical analysis of measurement uncertainty were inadequate for detecting slow accumulation processes that could create criticality hazards over extended operating periods. The facility modifications implemented in response to the incident represented a fundamental shift from concentration-based criticality safety to geometry-based safety, reflecting the lesson that complex chemical processes could systematically defeat assumptions about material distribution and concentration. The design of geometrically favorable dissolvers and feed tanks for filtration and solvent extraction operations ensured that criticality would be prevented regardless of plutonium concentration or chemical form. This approach eliminated dependence on procedural controls and administrative limits that could be defeated by process chemistry or operational modifications. The installation of borosilicate glass Rashig ring neutron absorbers in large auxiliary vessels provided an additional safety barrier that would prevent criticality even if plutonium accumulated in concentrations far exceeding design basis assumptions. These neutron absorbers, positioned to remain effective regardless of solution levels or mixing patterns, created inherent safety characteristics that could not be defeated by process chemistry or operational errors. The decision to implement both geometric control and neutron absorption demonstrated a defense in-depth approach that addressed the systematic vulnerabilities revealed by the incident. The blocking of supplemental transfer lines eliminated the possibility for unauthorized or inadvertent material transfers that could bypass safety analyses and create unexpected accumulation patterns. The investigation had found that the transfer operations preceding the December 30 incident, while consistent with general procedural guidance, had created material combinations that exceeded the scope of safety analyses for individual process vessels. The physical blocking of non-essential transfer paths ensured that future operations would be constrained to configurations that had been explicitly evaluated for criticality safety. The enhanced radiation monitoring systems installed throughout the facility reflected lessons learned about the importance of real-time detection capabilities for identifying abnormal plutonium accumulations before they could create criticality hazards. Gamma-sensing radiation alarms, with improved sensitivity and coverage, provided continuous monitoring of process areas for conditions that might indicate material buildup beyond expected levels. These systems were designed to detect accumulation patterns early in their development, enabling intervention before critical configurations could be approached. The improved portable survey instruments acquired for detecting plutonium buildup in process equipment enabled systematic monitoring of material retention in locations where permanent instrumentation was not practical. These instruments, calibrated specifically for detecting plutonium gamma signatures in processing environments, provided the capability for routine surveys that could identify accumulation trends before they became safety significant. The survey program developed in conjunction with these instruments established systematic inspection schedules and response criteria for managing identified accumulations. The comprehensive review of criticality safety training programs resulted in enhanced emphasis on the mechanisms by which normal operations could create unexpected hazards, moving beyond the traditional focus on preventing known accident scenarios to developing analytical skills for identifying new or evolving risks. The revised training included detailed case studies of the December 30 incident and similar events, with emphasis on understanding how conservative assumptions could be systematically violated through the cumulative effects of routine operations. This approach aimed to develop operational awareness of dynamic risk factors rather than reliance on static safety boundaries. The regulatory implications of the incident extended beyond the specific technical lessons to encompass broader questions about the adequacy of safety oversight systems that relied primarily on procedural compliance rather than continuous verification of safety assumptions. The Atomic Energy Commission's investigation found that existing oversight approaches, while effective for ensuring compliance with established procedures, provided insufficient capability for detecting the gradual evolution of conditions that could create new hazard profiles outside the scope of original safety analyses. The development of improved nuclear safety oversight reflected recognition that complex technical systems could evolve in ways that systematically defeated conservative design assumptions, while remaining within the bounds of approved operational procedures. The enhanced oversight approach emphasized continuous validation of safety assumptions through independent technical assessment rather than exclusive reliance on procedural compliance monitoring. This shift represented acknowledgement that administrative controls alone were insufficient for managing the dynamic risks present in complex nuclear operations. The long-term scientific contributions of the December 30 incident included significant advances in understanding the behavior of liquid fissile systems under dynamic conditions, with implications for both reactor safety and nuclear processing operations. The detailed documentation of the incident sequence, from initial configuration through nuclear excursion to stabilization, provided unique experimental data for validating theoretical models of criticality physics in complex geometries and chemical environments. These data supported improvements in computational methods for criticality safety analysis an enhanced understanding of the coupling between hydrodynamics and nuclear kinetics in liquid systems. The incident's influence on subsequent nuclear facility design and operation extended throughout the industry, with the lessons learned incorporated into regulatory guidance, industry standards, and facility-specific safety analyses. The demonstration that dilute concentration limits could be systematically defeated by normal chemical processes led to widespread adoption of geometry-based safety approaches for processing facilities. The recognition that mass balance accounting systems could mask gradual accumulation patterns resulted in enhanced material accountability requirements and improved methods for detecting retention trends. The December 30, 1958 criticality incident ultimately validated the fundamental principle that conservative safety assumptions must be continuously verified rather than simply implemented through initial design and procedural controls. The facility had operated successfully for 7.5 years under assumptions that proved inadequate when subjected to the cumulative effects of normal processing chemistry and routine operational modifications. The incident demonstrated that complex systems require active verification of safety assumptions rather than passive reliance on historical performance, establishing principles that continue to guide nuclear safety practices decades after the event.